We hear all the time about hydrogen, right? It's supposed to be the clean fuel of the future. But there's this massive kind of hidden challenge we have to solve before we can actually build that future. It's this tiny, invisible battle happening on a microscopic scale inside the very steel we need for all the pipes and tanks. So let's dive in and see what's really going on.
So what is this big problem? What is steel's invisible enemy? Well, the answer is kind of crazy. It's hydrogen itself. Yep, the very fuel we want to move around can actually become this saboteur, attacking the infrastructure that's meant to contain it.
And this whole phenomenon has a name: hydrogen embrittlement. Okay, so get this. Individual hydrogen atoms, the smallest atoms in the entire universe, are literally tiny enough to sneak inside the crystal structure of steel. And once they get in there, they act like millions of invisible little wedges, prying the metal apart from the inside out. It makes the steel super fragile and dangerously brittle.
All right, so here's how we're going to break down this whole puzzle. First, we'll dig into hydrogen's invisible threat. Then, we'll look at a new breed of steel that's designed to fight back. We'll see how scientists are forging the future and what they're finding under the microscope. And finally, we'll tie it all together with building the hydrogen economy.
Okay, let's jump right into Section 1, hydrogen's invisible threat. We're really getting to the heart of the problem here. Why this fuel of the future is such a headache for the materials we have right now. So here's the thing, the whole vision of a hydrogen economy. I'm talking everything from the big production plants to the fueling stations. It all depends on this huge network of steel pipes, steel tanks, and steel vessels. But the regular high-strength steel we use for stuff like natural gas, it just can't handle it. It's way too vulnerable to that embrittlement we were just talking about. And that is a massive engineering and, frankly, a huge safety problem.
Which, brings us right to Section 2, a new breed of steel. If the old materials aren't going to cut it, well, you've got to invent new ones. Scientists are basically designing an alloy from scratch that can actually stand up to hydrogen.
And this is the core of that new formula. Researchers are zeroing in on this special kind of lightweight, high-strength steel alloy. The base ingredients? Iron, manganese, aluminum, and carbon. You can think of this as the starting recipe for our new hydrogen-proof material.
And this is how they figure out the perfect mix. It's super methodical. They start with that base alloy, just to see how it performs. That's their baseline. Then, as you can see, they start tweaking it. They'll make a batch with a little nickel added, then another with some chromium, then another with a bit more aluminum, just to see exactly how each new ingredient changes the steel's ability to resist hydrogen.
So that takes us right into Section 3, forging the future. Because it turns out the recipe is only half the story. It's not just what you put in the steel, it's how you cook it that really makes all the difference.
Okay, so this diagram might look a little complicated, but it's basically the master plan. It shows this super precise, multi-stage process of heating the steel up to just the right temperature, squishing it under enormous pressure, that's the rolling part, and then cooling it down very carefully. Every single step here is designed to mess with the steel's internal structure on a microscopic level.
Let's just walk through it real quick. First up, homogenization. You're baking it at 1200 degrees Celsius to get a perfect, even mix of all the ingredients. Then comes hot rolling, where you squeeze the steel to start shaping its internal grains. After that, there's solution treatment and a quick cool down, followed by cold rolling and a final heating process called annealing. Every one of these stages is a deliberate step to build and refine the steel's internal architecture. You're basically programming it to be tough and resilient.
So after all that work, how do they know if it actually worked? Well, that brings us to Section 4, under the microscope. This is where the scientists get to look deep inside the metal and read its internal fingerprint. And this is what they see. How amazing does that look? This is the steel's microstructure. It's not just one solid thing. Those different colors are actually different crystal structures or phases. In this case, the blue stuff is a phase called austenite that gives it toughness, and the red is a phase called ferrite, which gives it strength. Getting the perfect balance and arrangement of these two is the secret to making the steel hydrogen resistant.
And this comparison right here really shows you the payoff of that whole forging process. On the left, you've got a microstructure with these really fine, complex grains. But look at the picture on the right. After one of those specific heat treatments, the grains have grown and become much more uniform. So by controlling the process, the scientists can literally design the steel's internal fingerprint, which is just incredible.
So all of this leads to a really critical question for the researchers. With all these different phases and variables in play, what's the perfect temperature to create the absolute best structure?
And that's where a chart like this comes in. Think of it like a weather map, but for steel.
It's a model that predicts how those internal phases are going to shift and change as the temperature goes up and down. Each of those colored regions represents a different phase. By studying this map, scientists can pinpoint the exact temperature sweet spot to get that perfect mix for maximum strength and hydrogen resistance. And that brings us to our last section, where we get to zoom back out and see how all this super detailed microscopic research actually connects to the real world.
You know, this isn't just theory. This is happening right now. Projects like H2 Future at the University of Oulu in Finland are doing this exact kind of fundamental research. They're laying the scientific groundwork that's going to make a global hydrogen infrastructure even possible.
And listen to how the researchers themselves put it. They say their work is trying to address this gap, offering novel insights into the metallurgical intricacies of hydrogen embrittlement, which is a very sciencey way of saying they're writing the rulebook for the next generation of materials we need for clean energy.
And this is why it all matters. All of this deep, complicated material science. It really boils down to something super simple and tangible for all of us. Safer, stronger, more advanced steel means a safer, more reliable, and a more efficient hydrogen infrastructure, period. This incredible research is solving the material problems we have today. And that just leaves you with one final thought, doesn't it? With these new materials, what new possibilities for a clean energy future are we going to be able to build tomorrow?